In the vast and enigmatic expanse of the cosmos, few phenomena capture the imagination, quite like the violent birth of a black hole through a hypernova. These extraordinary cosmic events represent the most extreme manifestations of stellar death, where the fundamental laws of physics are pushed to their absolute limits. A hypernova is an extraordinary astronomical event that represents the most powerful type of stellar explosion known in the universe. Unlike a typical supernova, a hypernova releases an almost incomprehensible amount of energy, so intense that it can be observed from the opposite side of the observable universe. These cosmic explosions occur when the most massive stars in existence reach the end of their life cycle, triggering a catastrophic collapse that gives birth to some of the most mysterious objects in the universe: black holes. Black holes are regions in space where gravity is so intense that nothing, not even light, can escape its gravitational pull. Formed from the remnants of massive stellar cores, these cosmic singularities represent the ultimate transformation of matter. At their core, they contain a point of infinite density where the known laws of physics break down, creating a cosmic phenomenon that challenges our understanding of the universe. The relationship between hypernovas and black hole formation is a testament to the universe's most dramatic process of stellar evolution. When a star with more than 30 times the mass of our Sun exhausts its nuclear fuel, it undergoes a catastrophic collapse. This collapse generates an explosion so powerful that it can briefly outshine entire galaxies, releasing more energy in mere seconds than our Sun will produce throughout its entire lifetime. These cosmic events are not just spectacular displays of destruction, but crucial mechanisms for the creation and distribution of heavy elements in the universe. Through hypernovas, elements heavier than iron are forged and dispersed across space, contributing to the complex chemistry that ultimately enables the existence of planets and potentially life itself. Join us on this extraordinary journey of cosmic discovery to explore the most violent and transformative events in the universe. Don't forget to like the video, subscribe to the Exploring the Universe channel, and share your thoughts on these mind-bending astronomical phenomena. Supernovas and hypernovas represent two extraordinary cosmic explosions, with critical distinctions defining their unique characteristics. While both involve massive stellar deaths, hypernovas are exponentially more powerful, representing the most energetic events in the universe. A standard supernova occurs when stars between 8 and 30 solar masses collapse, releasing tremendous energy. In contrast, hypernovas emerge from extraordinarily massive stars exceeding 30 solar masses, generating explosions approximately 100 times more energetic than traditional supernovas. Nuclear fusion in these massive stellar giants follows a complex progression. These stars continuously transform lighter elements into progressively heavier ones through a sequential fusion process. Hydrogen fuses into helium, then helium into carbon, carbon into oxygen, and so on, creating progressively denser and more complex elemental cores. As these massive stars progress through fusion stages, they create increasingly heavy elements, ultimately producing an iron-rich core. Iron represents a critical turning point in stellar evolution because it cannot undergo further fusion reactions that generate energy. This limitation triggers the most dramatic phase of the star's existence, gravitational collapse, when the iron core reaches approximately 1.4 solar masses, the Chandrasekhar limit. Fundamental physical processes dramatically change. The star can no longer support its own weight through nuclear fusion, causing a catastrophic gravitational implosion. In mere milliseconds, the core collapses, releasing an unimaginable amount of gravitational potential energy. This instantaneous collapse generates immense temperatures and pressures, creating conditions so extreme that protons and electrons are forced together, forming neutrons. The core's sudden compression triggers a massive shockwave that propagates outward, ripping the star apart in a hypernova explosion. The resulting event produces relativistic jets of matter and energy traveling at near light speeds, capable of being detected across vast cosmic distances. These jets can potentially generate gamma-ray bursts, signaling the birth of a stellar mass black hole. This magnificent process represents not just destruction, but cosmic creation, producing heavy elements and potentially seeding future stellar generations with complex chemical building blocks, essential for planetary formation and ultimately the emergence of life itself. In the cosmic theater, massive stars perform a dramatic final act characterized by an intricate and violent process of nuclear exhaustion and gravitational collapse. These stellar giants, with masses exceeding 30 times that of our Sun, undergo a profound transformation as they approach their ultimate destiny. The journey begins with the progressive depletion of nuclear fuel. Throughout their lifetime, these massive stars continuously fuse lighter elements into increasingly heavy ones, creating a layered structure resembling an onion. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and progressively heavier elements form concentric layers within the stellar core. As nuclear fusion progresses, the star produces ever more complex elements, ultimately reaching iron, a critical turning point in stellar evolution. Iron represents a fundamental threshold because it cannot generate energy through fusion reactions. Unlike previous elemental transformations that released energy, iron fusion requires energy input, disrupting the delicate balance that has sustained the star's structure. The iron core becomes a pivotal point of stellar destiny. When it reaches approximately 1.4 solar masses, the Chandrasekhar limit, the star loses its ability to counteract gravitational pressure. This triggers a catastrophic gravitational collapse, where the core implodes with extraordinary speed and intensity. In mere milliseconds, the core's density increases exponentially. Temperatures and pressures rise to unimaginable levels, forcing protons and electrons to merge into neutrons. The sudden, violent compression generates a massive shockwave that propagates outward, tearing the star apart in a hypernova explosion. This gravitational collapse represents more than mere destruction. It is a transformative cosmic process that births new elements, generates powerful relativistic jets, and potentially creates a stellar mass black hole. The iron core's collapse marks the final, most dramatic moment in a massive star's life cycle, symbolizing both the end of one cosmic chapter and the potential beginning of another. The hypernova represents the most violent stellar explosion in the universe, a mechanism of extraordinary cosmic proportions that defies conventional understanding of energy release and matter transformation. The hypernova's core mechanism begins with the gravitational collapse of a massive star's iron-rich core. When the core exceeds the Chandrasekhar limit, it implodes instantaneously, generating temperatures reaching billions of degrees. This sudden compression triggers a catastrophic shockwave that rips the stellar structure apart in milliseconds. A hypernova releases an incomprehensible amount of energy, approximately 100 times more powerful than a standard supernova. In mere seconds, it can emit more energy than our Sun will produce throughout its entire 10-billion-year lifetime. This energy release is so intense that it can be detected across vast cosmic distances, illuminating regions of the universe normally shrouded in darkness. The most distinctive feature of a hypernova is its relativistic jets, narrow beams of matter and energy traveling at near light speeds. These jets can extend millions of light years, carrying heavy elements and intense radiation, traveling at approximately 99.9% of light speed. These jets represent the universe's most powerful cosmic engines, capable of piercing through interstellar space with unimaginable force. We challenge you to share your thoughts. Can you imagine an explosion 100 times more powerful than a typical supernova? Drop your comments below, smash that like button, and subscribe to Exploring the Universe to continue exploring the most mind-blowing cosmic phenomena. What aspect of hypernovas amazes you the most? Their incredible energy, their role in creating heavy elements, or their potential to form black holes? Black holes emerge from the gravitational collapse of massive stellar cores during hypernova explosions. When a star exceeding 30 solar masses exhausts its nuclear fuel, its core implodes catastrophically, creating a region of space with such intense gravitational pull that nothing, not even light, can escape. The event horizon represents the critical boundary around a black hole beyond which no information or matter can return. This cosmic point of no return marks the absolute limit of the black hole's gravitational influence. Once anything crosses this boundary, it is permanently trapped within the black hole's gravitational domain. At the black hole's center exists a singularity, a point of infinite density, where all the star's mass is compressed into an infinitesimally small space. Here, the known laws of physics break down completely. Gravitational forces become so extreme that our current mathematical models cannot fully describe the phenomena occurring within this region. To form a stellar mass black hole, a star must exceed a minimum mass threshold. Typically, this requires an initial stellar mass of at least 20-30 solar masses. When the collapsing core reaches approximately 3 solar masses, it inevitably transforms into a black hole. Below this mass, the stellar remnant might become a neutron star instead of a black hole. The birth of a black hole represents one of the most profound transformations in the universe, a moment where matter is compressed beyond comprehension, creating a cosmic entity that challenges our fundamental understanding of space, time, and physical reality. The most powerful hypernova recorded is GRB 080916c, detected in 2008. This extraordinary event released an estimated energy equivalent to 9x1047 ergs, making it the most luminous cosmic explosion ever observed. A single hypernova can release more energy in seconds than our Sun will produce in its entire 10 billion-year lifetime. The energy output can reach up to 10^52 ergs, comparable to converting the entire mass of a star into pure energy via Einstein's famous E=mc2 equation. Compared to other cosmic events, 100 times more powerful than standard supernovas, brighter than entire galaxies during peak luminosity, capable of generating gamma-ray bursts visible across billions of light-years. Hypernovas are extremely rare in our galaxy. Scientists estimate only 1 to 2 hypernovas occur per million years in the Milky Way. This scarcity makes each observation a significant scientific event, offering unprecedented insights into stellar evolution and cosmic dynamics. These cosmic explosions represent not just destruction, but fundamental processes of elemental creation and universal transformation. GRB 080916c, detected in 2008, represents the most powerful hypernova recorded. Observed by NASA's Fermi Gamma Ray Space Telescope, this event released an unprecedented amount of energy, providing critical insights into extreme cosmic phenomena. Modern astronomical research employs sophisticated observation techniques across multiple electromagnetic spectrum wavelengths. This approach allows scientists to capture comprehensive data about hypernova events, revealing details invisible to single wavelength observations. Space-based observatories like Hubble, Chandra, and James Webb Space Telescope have revolutionized hypernova research. These instruments provide unobstructed views of cosmic events, detecting radiation and electromagnetic signals impossible to observe from Earth's surface. Recent theoretical developments challenge traditional understanding of black hole formation. Scientists now propose more complex models suggesting Potential multiple black hole formation mechanisms, role of initial stellar rotation in black hole characteristics, possibility of intermediate mass black hole creation, impact of stellar metallicity on collapse processes. These discoveries continuously reshape our understanding of the most extreme cosmic events in the universe. Hypernovas and black hole formations provide critical evidence for gravitational waves, ripples in spacetime predicted by Einstein's general relativity. These waves represent fundamental disturbances in the fabric of the universe, carrying immense scientific significance. The Laser Interferometer Gravitational Wave Observatory made groundbreaking detections of gravitational waves generated by massive stellar collapses. First confirmed in 2015, these observations directly validated Einstein's century-old theoretical predictions about space-time dynamics. Hypernova research pushes the boundaries of theoretical physics, challenging and refining our understanding of quantum mechanics, extreme matter states, fundamental force interactions, cosmic evolution mechanisms. Observations of hypernovas and black hole formations provide empirical evidence supporting Einstein's theories of relativity, demonstrating the profound connection between theoretical predictions and observable cosmic phenomena. Challenge for viewers. Can you imagine an explosion 100 times more powerful than a typical supernova? Share your thoughts and perspectives in the comments below. What aspect of these cosmic events amazes you most? Their incredible energy, their role in creating heavy elements, or their potential to form black holes? Hypernovas and black hole formations are crucial to comprehending universal evolution. These cosmic events reveal fundamental processes of matter transformation, energy conversion, and the interconnected nature of cosmic structures. These stellar explosions serve as cosmic foundries, generating elements heavier than iron that are essential for planetary formation and life. Elements like gold, uranium, and platinum are created during these extreme stellar deaths, dispersing complex matter throughout the universe. Our very existence is intimately linked to these cosmic events. The elements comprising our bodies, carbon, oxygen, nitrogen, were forged in the hearts of massive stars and distributed through hypernova explosions. We are, quite literally, made of stardust, created by these violent cosmic processes. These phenomena demonstrate that we are not separate from the universe, but an integral part of its grand, ongoing narrative of creation and transformation. Hypernovas represent the universe's most extreme stellar events, revealing critical insights into cosmic evolution, black hole formation, and elemental creation. These phenomena demonstrate the interconnected nature of universal processes, showing how stellar deaths contribute to the continuous cycle of cosmic creation. Humanity occupies a remarkable position in the universe, not as external observers, but as integral participants in a grand cosmic narrative. The elements comprising our bodies were forged in the violent hearts of massive stars, distributed through hypernova explosions billions of years ago. Dive deeper into the mysteries of the universe. We invite you to like this video, subscribe to Exploring the Universe channel, share your thoughts in the comments, explore the mind-bending complexities of cosmic evolution.